types of problems quantum algorithms can solve, how they relate to cryptography, and also maybe mention some problems that maybe we can find quantum algorithms for in the next 5 to 10 years. So that's sort of what I'm going to try and do. So I'll start with problems that have quantum algorithms. So here we're looking for exponential speedups compared to the best classical algorithm. So of course that starts with Schwartz factoring algorithm and discrete log, algorithm for discrete log, and the related crypto systems there are RSA and Diffie-Hellman. So after he found these algorithms in 1994, some of the most obvious questions people were looking at, there are quantum algorithms for lattice problems. That's still an open question. Graph isomorphism, what else can we find? The next exponential speedup that we found was for Pell's equation. So, if you're curious, in this equation you're given a positive non-square integer d. You want to find integers x, y, such that x squared minus 3y squared equals 1. And there were some other associated problems that were also solved, like the principal ideal problem in the class group. Now, from a quantum algorithms perspective, we're just trying to find any problem we can solve. But it turned out there was also a key exchange system, the Buchmann-Williams key exchange system, that was based on the hardness of this. And part of their motivation for developing it was, in case there was a classical polynomial time algorithm for factoring, hopefully their system would still be secure. But in the realm of quantum computation, it's not secure. And then, after a while, we found quantum algorithm for computing the unit group of a number field. And this ended up having a connection to a special case lattice problem that I'll talk a little bit about later. And it's related to some crypto systems, soliloquy, a certain fully homomorphic encryption scheme, and multilinear maps. And plus there are some other number theoretic problems, like problems from function fields, like discrete log and the divisor class group, computing Hilbert class fields of certain types, and so on. So these are the problems, though. You have an input, an output, it's going. You can analyze everything. So, yeah.
Do I correctly observe that these are all classical input, classical output problems?
These are all classical input, classical output, yes. So in order to get more understanding of any computational model, another way to approach it is through oracle problems, and there are a list of also oracle problems that have exponential speedups. So no classical input, just an oracle that you can query. That started with the recursive Fourier sampling problem by Bernstein and Vazirani, which gave the first super polynomial speedup of quantum computers versus the best randomized algorithm. And then Simon's problem, which was a very important one also. So here you're given some function on this group, z2 to the n, to some set, and it hides a subgroup in a certain way, and your goal is to compute this subgroup. And it's an oracle problem, and so Peter Shor said he was reading Dan Simon's paper, and he saw that this was finding hidden periodicities. Not the way I first looked at it, and that was part of his path to getting to the factoring algorithm with Simon's paper. It's also interesting because I talked to Dan Simon, and I was like, I have this, we had found a hidden shift algorithm, and I was excited to talk to him about it, but he wasn't super interested, and he's like, so I asked him, Dan Simon, where did you come up with Simon's algorithm? And he said, well, I was in graduate school, and I really didn't like quantum computing. And I was trying really hard to show that quantum computers are useless. But then I came up with this problem, and he showed an exponential separation. So I guess maybe you can keep that in your toolkit for algorithm development. I like them. Okay. So then the next problem was there's a sort of a different type of problem, finding hidden shifts. So this one was first based on the Legendre symbol, called the shifted Legendre symbol problem. So the Legendre symbol tells you whether or not a number is a square mod p. So it's 1 if it's a square mod p and -1 otherwise. So if you think of filling in the array of all the Legendre symbol values, you get 1s and -1s, half of each, because half the numbers are squares. And in this problem, you're given a cyclically rotated version of this vector, and your goal is to find the shift. So you're given f of x, which is the Legendre symbol of x plus s. So we found a polynomial time quantum algorithm to solve that. This has some relation to crypto, not directly, but It's been suggested to, for pseudorandom bits, you could pick a random spot in this array and output like a poly-length sequence. So it's a little bit different because you don't have access to as much data. But still, yeah. Okay, so these are sort of two of the things we look for in general, quantum algorithms when we're trying to solve problems. Are there hidden periodicities? Are there hidden shifts of a certain type? This was extended to work on bent functions by Martin Berthelot and others. And then it's actually been so the algorithm working with bent functions has been implemented on 5 quantum bit computers and also 11 to sort of benchmark how well their machines are working. And then I'll give one more example. This one is not related to crypto yet. Maybe it will be at some point. So this is the glued trees algorithm. So here you have an exponential size graph. And what you can do is query a vertex and get the names of the neighbors of the vertices. And the graph has a special structure. So there's a binary tree on the left and a binary tree on the right. And then you connect the leaves with a random cycle. So you're just trying, and then what you're given the name of the entrance vertex, and you're trying to get to the exit vertex. So if you start, you can query the entrance and you get the neighbors, and then you can sort of go along the tree up to the middle, and then a classical algorithm gets lost in this cycle. And there's this quantum algorithm they found as a random walk where it starts the superposition of the entrance, and then second level, third level, and it just kind of moves left to right, magically through the middle, and gets you the exit node. Still is open how to find a path, last I heard. We don't know how to find a path from entrance to exit. And then there's some other problems, hidden radius problem outside polynomial hierarchy. So these are the main exponential speedups we know of, outside of simulating physical systems, quantum mechanical systems, which is the other application area. All right, so post-quantum cryptography, we've been hearing about this. So our goal is to find and use crypto systems that are secure against quantum computers. We're talking about finding classical crypto systems. And in cryptography, what that requires is a hardness assumption, right? So decryption should be hard, so we need some problem that's hard for computers to solve, and we don't have techniques to prove lower bounds. So what we have to do is assume some problem is hard, and we need to somehow gain confidence that there is no algorithm for some problem. So as I mentioned, some problems have been ruled out, and then in this NIST standardization process, there are some leading contenders with lattice problems, isogeny problems, coding-based problems, and multivariate polynomials. We need to figure out which of these are hard for quantum computers to solve. And I'll just mention, I'm not going to talk about it in this talk, but another area for post-quantum cryptography is when you're dealing with cryptographic protocols. So even if you have some cryptographic hardness assumptions, like suppose you assume there's no quantum algorithm for a lattice problem, when you design cryptographic protocols, you need to then have a security proof for that assumes the adversary is quantum. And in general, the proof shows, like, if you break the protocol, then you break the cryptographic hardness assumption. And that requires a separate proof in addition to the assumption. Okay, but I want to focus on hardness assumptions in this talk. So in this standardization process, they're asking for public key encryption, chems, and digital signatures. And as far as motivation, why are they doing it now? They say, for one thing, there's been noticeable progress on building quantum computers. And the second thing is it takes a lot of time to develop, standardize, and deploy systems, so you need to start early. So for one thing, if we start with deploying systems, it's easy to test new systems, right? When you think like, okay, how hard is it to replace crypto? I think, well, I hit download new browser, and then I'm good. But that's only for testing new systems. What's hard is getting rid of all of the old stuff. So for example, in this National Academy's report that Dan was talking about, they pointed out that it took 10 years for Microsoft to get rid of MD5, which was broken in 2005, through a software update. You have to make sure that people can replace what they're using with something else. And then another thing that Dan mentioned was, some things you need to stay encrypted for a long time, like national security documents, health data. So there's a problem if I'm going to encrypt my health data today, I want it to stay encrypted for 20 years or longer, forever basically. So I need to encrypt it today with post-quantum crypto. I shouldn't be using RSA to encrypt it. So I already need to know what the new crypto systems are I should be using. So that's deploying. Deploying takes a long time. Also developing new systems. So what are we going to replace our current system with? That also takes a long time. Right? So like, how do we show systems are secure? Can't prove lower bounds on problems. So the best we can do is like try really hard, not break it, or what's common is to show that breaking a crypto system is related to some well-studied hard problem. For example, with RSA, it's related to factoring integers. We know if we can factor, we can break RSA. And we look for these functions that are easy in one direction and hard in the other. So, for example, if you take two large primes p and q, it's easy to multiply them, but this factoring problem of going from right to left here is hard. So, we have to decide when are we confident that a problem is hard to solve. For factoring, as we heard, well, I don't know if we heard, okay, we heard that about lattices. So for factoring, there's a similar answer. It's been studied for centuries, and no fast algorithm has been found. Seems like a nice argument. But, I think we do have to be careful a little bit. I mean, even in factoring, there was kind of this surprise, I think in the late 80s when the number field sieve was discovered. So the running time, the best classical algorithm ran in time like something like 2 to the n to the 1/2. And then the number field sieve was discovered, and it brought it down to something like 2 to the n to the 1/3. So it still is an exponential time algorithm, but that changes the key sizes you have to use by a lot when the exponent goes from square root n down to cube root n. Okay, but so in post-quantum, we're not going to use factoring anyway. So where do we look for hard problems for crypto? So if we start looking at around NP, and I'll blur the distinction between function problems and decision problems, so we're looking for something without an efficient algorithm. So we don't care about polynomial time. We can't use those. NP complete would be sort of the first natural reaction, but as far as we know, those are pretty hard to use. There's some evidence with theoretical results showing that if you could base crypto on NP-complete problems using specific types of reductions, the polynomial hierarchy collapses. And actually, in the NIST proposal, these multivariate polynomials are using special cases of NP-complete problems. But the problem is, one of the problems is NP-completeness is a worst-case notion. You're only guaranteed there's one hard instance per each input size. In cryptography, you need to be able to pick random keys. So if you pick from a random distribution, they all have to be hard. And there's a mismatch there. So what ends up happening is we look in this class, sometimes called NP intermediate, where we look for problems that aren't NP complete, aren't polynomial time, and we see what we can do. So starting at the bottom, factoring discrete log, Pell's equation, other variations of that, lattice problems, isogenies, graph isomorphism encoding fits in there too. I didn't put it on there, but it's around there. So if we're looking for hard problems for crypto, classically this picture makes sense. But if we retell the story for quantum, now we want to figure out which of these problems also do not have quantum polynomial time algorithms. So it started, you have to rule out using factoring and discrete log, then Pell's equation, Buchman-Williams key exchange system, and then finally, we finally worked for more than 10 years and got the unit group and arbitrary degree. And one interesting thing happened at this point, which is one of the special case lattice problems fell down, and there was a link between the unit group and this, and I'll try and tell you a little more about that. And so that'll be quantum algorithms, and then after I am done with that, I'll tell you about something where we don't have any exponential speedups yet, but somewhere where we may be able to find exponential speedups in the next 5 to 10 years, which is isogenies.
What is your opinion about where things like dihedral hidden subgroup fit in this big map?
Where does dihedral hidden subgroup fit? It's outside quantum polynomial time right now. It's an oracle problem. So
it works with isogenies, right?
I mean, it's with one type of assumptions.
yeah, I don't have oracle problems written down on this, so I don't. It's related to things,
But you would guess it's close to your curve.
oh, I don't know where it is. I know where it is today. I don't know where it belongs. This is not like the final line necessarily. So right now it's on this side. Or maybe it solves a sub-piece of some problem. Like it itself,
But it might still be useful for crypto.
Yes. Yeah. And it's used, okay. There is a sub-exponential time algorithm for isogenies using hidden shift, which is the dihedral hidden subgroup problem. So it is used for sub-exponential. And there are attempts to connect it to lattices that haven't worked because of technical problems. So it's floating around, but it's not on there. Okay, so first I'll tell you about this connection between the unit group and lattices. All right, so there's this general question, are there quantum algorithms for lattice problems? And this is still mostly open. First, I just want to tell you that that's not like a single question. It's not just like a quantum algorithm for a lattice problem. There are actually lots of different types of lattice problems and also different types of lattices. So the question gets more complicated. So if you haven't seen a lattice, here's an example of a two-dimensional lattice. It's a group in R to the n, discrete set of points. It's generated by a basis. So you might be given, say, two basis vectors, b1, b2, and the lattice is the set of all integer linear combinations. In a computational problem, the first one, shortest vector problem, is given a basis for the lattice, you would like to compute the shortest vector, so one closest to the origin, shortest non-zero vector. So there's the shortest vector problem, the closest vector problem. There are special cases of these where the crypto is actually, these are the problems crypto is actually based on, gap SVP and BDD, short generative principal ideal problem. And then there are other places lattices are used in not this sort of way, but there are things where there's a hidden lattice and you want to find the basis to begin with. Instead of the basis being the input, the question is what is a basis for the lattice?
Sorry, for that last problem, what is the input of the problem?
I haven't said.
Yeah, no, that's why I'm asking.
Anywhere you would like to use it. So we look for, when I was talking about finding hidden periodicities, right? The answer to that periodicity is a high-dimensional lattice. So in this case, I have the number field case in mind, which is what I'll talk about. But I mainly would just want to say that when you talk about lattices, it's very, if you're familiar with, if you work with lattices all the time, it's common just to think about this, but there are other problems where it's finding the basis of a lattice instead. So you have different problems. You also have different types of lattices. So this one I'm showing you here is an additive group. You can also put more structure on it and get a multiplicative group on top of it, use geometry from number fields. And so, when you're saying, is there an efficient quantum algorithm for a lattice problem, there are some different choices. Okay, so I want to tell you a little bit of a story about how we were working on quantum algorithms and other people were working on crypto, and they sort of intersected. All right, so what makes good crypto? So I'm taking these actually from the NIST call, so I didn't invent these myself. So you'd like a good theoretical basis for your crypto system. So for example, breaking the system should imply solving some hard problem, or it should at least be closely related to a hard problem, like factoring or lattices, solving a lattice problem. You want to have efficiency, so small key sizes, efficient algorithms for encryption, for decryption, for key generation. They also mentioned flexibility. You might want to have additional functionalities. You might want to have parallelization of the algorithms. Simplicity. There are more things I left off, but where do you get all of these things? So I'll tell you a little bit about the lattice story. So, way back when, it was hard to even find a random class of lattices that were hard, and ITI figured out how to do that in the late 90s. But it was hard to build crypto directly on these random instances. And what really changed that was in 2005 with Regev, when he showed that, so he defined a new problem, learning with errors, LWE, and he showed that if you can solve LWE, then you can solve worst-case lattice problems. And the reason why this was good was because it turns out that with LWE, it was much easier to build crypto on top of this than on top of lattice problems. And another thing I'll point out is, since it's quantum talk, so this reduction, this is my notation for a reduction, and the Q means it's a quantum reduction. So actually, the implication is that if you break one of these crypto systems, then there's a quantum algorithm to break a worst-case lattice problem. So this was really nice. There was this. So just to give you an sort of one step of his reduction, to show you where lattices and quantum come together. So this is a picture supposed to be a superposition over the dual lattice with Gaussians around each point of a certain radius, 1 over r. And we've known for a long time, if we could just compute this superposition, the thing you can do is compute the quantum Fourier transform, and it would then give you a distribution over the lattice itself with a Gaussian envelope with radius r. And when you measure this superposition, you'll get lattice vectors that are a length at most r. So to get a short vector over there, you need to be able to control 1 over r. And that's hard. And so what Regev did, which was really nice, is he used the LWE oracle, which you can think of as being closest vector problem if you're familiar with that, to create these superpositions. So with a closest vector problem oracle, you can do that easily. And so he showed that one round of this would get you down by a factor of square root 2, and then it's more complicated. You have to sample more vectors and then repeat this process many times to get a short vector. So this established a really nice theoretical basis for crypto based on lattices and quantum reduction. Okay, so we have this worst to average case reduction, learning with errors implies solving a lattice problem. So the next thing on the list I showed you before was efficiency. And here there was a little bit of a problem because the key size and the time to take were at least quadratic in the security parameter. And that's slower than people would like. So the solution to that was to start using lattices that were special case lattices. They have more structure that will make the algorithms faster. Okay, so here's the first one with Regev's, just lattices over the integers. And the next step was by Lubashevsky, Pikert, and Regev, where they took lattices that came from ideals in cyclotomic number fields, ideals inside the ring of integers, whatever that means. So instead of LWE, you have something called ring LWE. Now the lattices are actually rings inside. They come from rings, so there's also a multiplication. So there's an addition operation and a multiplication structure on the vectors in R to the n. And that brought the key size down to linear. And the algorithms got more efficient. You could use fast Fourier transforms and so on. So that's kind of where things are today. Now, I'll switch for a minute, and I'll tell you that sort of separately, we were thinking about just how do you compute the unit group of a number field. I'm not going to define what that is, but I'll just say that they were working in number fields, we were working in number fields. We were looking for a hidden periodicity. In that case, it's a lattice. I don't have a picture of the lattice we're looking for. There are several lattices that come up in these algorithms. So there's the lattice we're looking for. This is a lattice that's in the range of the function. So to find that hidden periodicity, I'll just tell you that you're working in the ring of integers, and there's a way to stretch the lattice on the algebraic norm lines that is periodic. The question is how do you use this? How do you implement this? How do you get anything to work? So it has the property that's periodic on the unit. So if you're familiar with the hidden subgroup problem, you need periodicity, you need one-to-one on the period. it satisfies this. But the challenge is to implement all this and get polynomial time in the degree. So for example, how do you even compute this function? E to the t is a doubly exponentially large number. You can't just compute it and multiply it times O. And so a lot went into this. One thing we needed to do was a new continuous hidden subgroup problem definition and an algorithm that solves that in high degree to handle noisy Fourier analysis. So we were over there doing that. So after 10 years, we finally solved it. And then something kind of surprising happened, where in this sequence of more and more specific lattices, there was another assumption made, where instead of just using ideals, they would pick principal ideals, and they would pick principal ideals with short generators, whatever that, you know what that means. And the reason they did that is it just gave more structure. And that more structure made it possible to implement some new things. There was a certain version of fully homomorphic encryption, multilinear maps. And what came out was there was this paper published by Campbell, Shepard, and Groves, where it's called Soliloquy, a cautionary tale. And they said, well, we were building this crypto system based on high degree number fields, and we broke it using a quantum algorithm. That was, so it turned out that this was sort of one assumption too many. And the pieces that go into that, so there's our unit group algorithm. That was extended to solve the principal ideal problem by JF and Fang and so on. And then the missing piece, so this let you compute some generator, but you're trying to compute some short generator. And the missing piece was a classical algorithm that they showed in their paper, well, that they said existed in their paper, for solving the bounded distance decoding problem in the unit lattice. So I'll just put up a picture showing you how all these pieces fit together. All right, so the input is an ideal. It has a short generator alpha, so it's somewhere near the origin. That's what you're trying to find. So the first step is to compute the unit lattice using the algorithm I talked about. Then you solve the principal ideal problem. So the principal ideal problem, so this is I is a principal ideal, so you get some generator beta for that ideal, but you can't control how long it is. And then you use this last step they pointed out, which is to solve bounded distance decoding. And that gets you to a unit, and then once you get a unit, you can adjust your generator by the unit to get a short one. And putting these together also gives you a 2 to the square root n approximation algorithm. So this is an example. Classically, we don't have any sub-exponential approximation algorithms for these, but the quantum algorithm gets it. So, so this is my story about lattices. I just wanted to tell you that, so in cryptography, it helps to make assumptions to make systems more efficient. The question is like, where's the line? When do you make too many assumptions? And it still is an important open question whether there are quantum algorithms for these other cases of lattices. All right, so that's the part that has quantum algorithms in my talk. And now I was going to tell you about, what type, an example of a set of problems that might have quantum algorithms in the future. And that is from isogeny. So we're really switching gears here. Sorry about that, but I have to talk about a different problem now. So one new possibility is to use a different way than what we've seen, say, with discrete log, to use elliptic curves. So usually what we're used to, at least what I'm used to, maybe not everybody in the room, but the hard problem you want to use for crypto is discrete log on the elliptic curve. So you pick an elliptic curve. There's a group law there. These are good compared to factoring because you get smaller key sizes. And, but Shor's algorithm can solve discrete log on this, so that's not helpful. So the new proposal is to use an exponentially large set of elliptic curves and the isogenies between them. So an isogeny is a map between elliptic curves. It's a homomorphism. And so far, we don't have any exponential speedups. Like I mentioned before, there's a sub-exponential time algorithm. But I think this is a good place to look for potential quantum algorithms. Let's see. So I'm not going to talk through this whole slide.
The sub-exponential thing, does that ruin the key size advantage that you had from the...
I don't know the direct comparison for key size comparison. Someone else here might know. Do you know? No. Yeah, Tanya?
So it's not in all isogeny-based systems. There's two families, and for SID it doesn't apply anyway, and for C-side it does apply, but C-side starts with a smaller basis, so then it depends on the security level, but it's still very small. The key size.
It's complicated. There are several systems, so I'm gonna try and show you that there are several different problems by putting up some pictures. And it only applies to a subset of those. So then you have to look at that subset and decide. So for this slide, I just want to say that there's a lot of crypto has been proposed, hash functions, key exchange, signature schemes, based on isogeny problems. There are algorithms for trying to solve these problems and other problems, using various levels of assumptions and also some provable. Okay, so I just want to try and give you some flavor of what these isogeny problems look like. So, I mentioned earlier, say with factoring, there's an easy problem and a hard problem, and given two integers, it's easy to multiply them, it's hard to factor them. So what's easy and hard in isogenies? Okay, so if I give you an elliptic curve, what's easy is to compute, say, degree 2 isogenies that are adjacent to it, or compute the degree 2 isogenies out of it. And so what that means is you can compute sort of neighboring elliptic curves with certain constraints. So given any elliptic curve, you can compute the neighbors. You can compute neighbors, so you can walk along a path where it amounts to concatenating isogenies, you're concatenating homomorphisms. Okay? So that's what's easy. Sort of a starting point to develop crypto systems. And what's hard is if you're given just, say, two elliptic curves. Suppose you're given E over there and you're given E prime here, and you're saying, give me an isogeny that connects those two. The assumption is it's hard to do that. That would correspond, say, a degree 2 to the n isogeny would be like taking n steps from E, but there's like an exponential search tree if you're just doing brute force. So how do you find where E is? E prime is.
Question?
Yeah.
Is there a related decision problem too? Like are two curves isogynous?
It's going to
The singular, yes.
But
Any-
not in general?
well, they are isogynous in that
Can
case.
split up into different, not any two ordinary curves are isogynous, but yeah, so if you look at the right subset of curves, you can guarantee that there is one of those things.
Interesting.
Okay. Just to make it slightly more concrete. So given two elliptic curves, they'd be described by these elliptic curve equations, working over some field. And you're trying to find, you can describe isogenies in different ways. One way is it's a rational map. So you take points x, y on that curve to f of x, y, g of x, y on the second curve. And each curve has an abelian group structure, and you're preserving that structure.
Oh, Sean, I should have also asked, I'm so sorry. Is the decision problem hard also?
It's equivalent if you put a length on, I mean, if you're trying to find a path in a graph with small degrees, then if you can decide whether there's a path of particular length, then you can use that to find a path.
I see. So they reduce to each other.
What is they?
The decision problem and your give me the isogeny problem.
I'm not going to say yes, because there are many variations of these problems. And I'm not sure if we're talking about the right one.
Not in all settings.
Not in all settings.
Put the right inputs in.
Yeah, you have to put the right
And
constraints on
yeah.
your sets and stuff.
So part of all of this work is trying to figure out which problems reduce to each other. And then it takes you have to be pretty careful with even defining the objects and what their size is and everything. So, in fact, figuring out, the complexity of all the variations is I think, I don't know. Nobody's written it down. I don't know if it's obvious or if, I don't even know what the open questions are. So we sort of took more initial steps of just what are the objects, how big are they, and so on. the problems reduced to one another. Okay, so one type, okay, there are two types of isogeny graphs. I'll put those on the next slide, but I just want to give you an example of supersingular, just to sort of, again, try and make it more concrete. So as I was telling you, you can compute the neighbors of a graph, of an elliptic curve. And if you imagine just doing that forever, you can construct a graph. And so this is what's called the supersingular L-isogeny graph. So the vertices are supersingular elliptic curves up to isomorphism. And then the edges are, so if you're talking about the L-isogeny graph, you connect them when there is an isogeny of degree L. And when you do that, the degree of each vertex is L plus 1. You get a graph. It's exponentially large. In this case, there are like p over 12 vertices. And given a vertex, given any vertex in the graph, you can efficiently compute its neighbors. In this case, in the supersingular case, this graph is also an expander. So you can do things like, pick random vertices by just taking a random walk in the graph. And so you may also, so one thing you'll see is this term pathfinding. So this problem of finding isogenies is the same as pathfinding. Given two vertices in this graph, find a path between them is the same as finding an isogeny. Although there are special cases. You can specify like how long the path is allowed to be and things like that. Okay, so as I mentioned, there are two types. So I just was talking about the supersingular case where the graph is an expander. You can efficiently sample from uniform vertices. The second case is called ordinary. This ordinary is the case where there's a sub-exponential time quantum algorithm for finding isogenies. Here, the structure is different. It's called a volcano. Kind of looks like that. It looks a little different. So while this is an expander, one thing to keep in mind is just like there's a really big cycle in the ordinary case. So the structure is different, and there's a group action in the ordinary case that you don't have up here that lets you sort of walk around these vertices and act on them. And that group action is what was used to find this, to set up a hidden shift problem to find the isogeny, say, between E and E prime on the same level. Okay, so. Now, as with the lattice case, people are interested in making these systems more efficient. I mentioned that there are lots of crypto systems being built on these hardness assumptions. So one thing you might want is more efficiency that's in the ordinary case, but you also want the group action. And so there's a proposal called CSIDH, where, so in this supersingular case, you can work everything is over fp squared. If you restrict your curves down to just fp instead of fp squared, you get a group action. The graph changes somehow, and now you also get the group action on this new graph. So everything gets more efficient. It's nice. But from say a quantum algorithm's perspective, or even classical algorithms, the question is like, is it secure? Once you're adding more structure, does that somehow make it better? And that applies to all of these. Okay, so Dan was talking about how secure is lattice-based cryptography. We don't know how secure is isogeny-based cryptography. It's too early to know against quantum or even classical algorithms. So our goal. Our goal is to try and find quantum algorithms for these isogeny problems. But like sort of look on the map, it's like you are here. It's like we're sort of way back at the beginning. We're just trying to understand, like I said, understand the objects in the algorithm, basic classical algorithms for working with these. And it gets complicated because isogenies, for example, have many different number theoretic descriptions. You can describe them as a subgroup of the elliptic curve, as an ideal, as this rational map that I showed you, that I talked about before. Some of these are algebraic, some of these are geometric. And so there's really a lot of objects flying around to work with. And some of the computational challenges that come up, so the elliptic curves can be defined over a small field. but all the tools you're using to work with them, like torsion groups, the isogenies themselves, are defined over the algebraic closure. And so you have to be careful that your coefficients of all these objects aren't blowing up, becoming exponential size, for example, or your algorithms won't run in polynomial time. Now, if you do start looking at this, you'll see there are 3 basic hardness assumptions related to this. There's the first one, which is computing isogenies that I mentioned. There's one called computing endomorphism rings. These are isogenies back to the same one. So this amounts to like computing cycles in that graph. So you think it's kind of related to finding paths. You're finding cycles. And computing maximal orders. So I'm just going to give, I'll give one example here of a place where, just try to give you a simple example where structure can help. The underlying number theory can help in solving a problem. So one of these problems I mentioned was finding cycles in these graphs. This is an important subroutine. It takes exponential time. And the generic way to do it is just to sort of sample random paths until you get a collision. And if you pick a path and you keep sampling paths, eventually you'll have a collision. By the birthday paradox, it takes square root. There are p vertices, so it's square root p number of paths you take, and then you concatenate your 2 paths and you get a cycle. So this requires square root p time and square root p space. If you just ignore the number theory other than using the fact that it's an expander. But if we use some more underlying structure, it turns out we can reduce the space requirement down to be polynomial. So there's an observation. If you find what are called conjugate pairs that are connected by an isogeny, you get a cycle out of that automatically. So we proved that the fraction of curves that are adjacent to their conjugate pairs is 1 over square root p. So if we can sort of get any of these vertices in this 1 over p fraction of the whole graph, we can get a cycle. So there we just sample, and now we don't have to keep track of our paths to use the birthday paradox. We just need one path that gets in there. We forget them as we go. And so here again, the algorithm is just take random walks to get a random vertex in the graph, and then you form this cycle. So that's still square root p time, but down to log p space.
It's a classical algorithm.
Classical, yep. Okay, so just to summarize my talk, quantum algorithms and classical post-quantum cryptography are sort of intimately tied together. Some people are trying to develop post-quantum crypto. Some of us are trying to just solve any problems we can with quantum algorithms. And this gives us a place to sort of go back and forth with developing systems, breaking them, maybe with a quantum algorithm. It's an important back and forth. We definitely need quantum algorithms to know how secure these systems are. First of all, we'd like to determine which problems are secure in theory, like meaning there's no polynomial time quantum algorithm, as far as we know. And then we have to understand it more concretely to choose key sizes. So you want to use the best exponential time algorithms you have, choose key sizes for those. And in general, these problems that are NP intermediate in general, but also these ones that come from some of the crypto systems with lattices, isogenies, coding theory, all the variations in there that provides a rich set of problems that we can use to try and develop new techniques for quantum algorithms. So we can start by looking for hidden periodicities and hidden shifts, but maybe among all these things, we also find something else we can do with quantum computing. Okay, I'll stop there. Thanks.
Do you have any questions?
I'm curious about something which may be a little off the wall. Maybe 2 decades ago, there was a lot of interest in physical one-way functions, using physical systems, for example, scattering of light off of paper to generate a one-way function, in the sense that it's very unlikely that you'd get the same scattering function with any other sheet of paper. And it was interesting because it utilized physical mechanisms to make cryptographic primitives that may or may not be quantum secure. I'm curious if you know of where this has gone, or if you've think that these might be even open to quantum algorithms. And
I haven't seen it. Is it actually quantum crypto?
this was classical crypto.
Classical crypto, but somehow based on light scattering and.
A quantum process in a physical system.
Dan might know.
So there's been papers over the last 5 years or so by Boris Skorich and collaborators on what are called quantum readout puffs. So a puff is a physically unclonable function, which was illustrated by what you were saying. Then a quantum readout puff is, well, you fire a superposition over to somebody's glass, which is optically scattering that superposition. I mean, you need to have your superposition of laser, for instance, or something that can interact with the device. And then it sends back the superposition of speckle patterns, which you then read in some random basis.
Right.
And then the point is that the device, unless, I mean, you could imagine if somebody could, clone this device by, observing how it's reacting to different angles, different polarizations and so on, different positions of the laser, and then they could build a quantum computer which could, read the lasers that you're firing at it, do the same computation without measuring it, send back the same results. You could imagine how somebody could clone it, but of course it would be building a super expensive quantum device that would do what a cheap piece of glass can do. So anyway, there's been various papers which are actually building this. And it does seem to achieve some security properties which are not easy to achieve in any other way that we know.
If I may continue, just to be clear, this is not an encryption system, it is a token.
Yes.
So it's like authentication or it's a key storage. You still need public key cryptography that Sean is talking of.
Yes, but it would give you digital signature schemes.
No.
No,
No?
no.
A signature is something that anybody can verify. Like you're submitting a piece of software with a signature.
No,
that
you'd have
anybody
to have the unclonable object in the library or something. So it would be a weird signature. Not digital.
If you just want signatures, isn't it known how to do that based on any one-way function? So
Yes,
I mean
Locale's 1979, right?
yeah. So I mean that the situation for quantum secure signature schemes should be much more solid even than that for public key crypto.
Well, I would actually suggest adding that to your target list.
Yeah.
That even though, I mean, it's easy to say, oh, sure, one-way functions are easy to build, and therefore we're good on signatures. Actually, it would be good for people to look at the proposed one-way functions, the hash functions that people have written down, and say, are there any ways to improve the attacks with quantum algorithms or just with regular algorithms? There's various people looking at that, but I think there's not enough quantum expertise looking at these targets.
Are there any other questions? At some point you said something along the lines of we might be 5 to 10 years away from quantum algorithms to solve isogenies. I mean it might be true for every primitive, but why did you pick isogeny specifically?
It's in my mind right now. I know so little about it that I'm confident we'll find something to do with it.
I have another question, which might be good lunchtime discussion fodder, which is, these are classical in, classical out with classical keys. And Daniel Gottesman and I played around with quantum keys for a little bit for our quantum digital signature scheme, but I haven't seen much follow-up along that direction. Do you think it's still interesting to think about quantum keys, for example?
Yeah, I mean, it's not something I've thought about. But anybody else has?
There are no other questions? So, Thomas has an announcement before we thank
we can
the
thank
speaker again.
Sean.
Okay, let's thank.
I just wanted to remind everyone that so we resume at 2 and there's a talk and so